So this image here is actually a similar one, but not exactly the same as to the one in your beta textbook. And I've just copied it from GeoGebra into here so I can draw all over it. Right. The story behind this is train tracks and Dunedin and some kind of train track that goes wherever else. I forget what city it is. And this is on the y-axis, the distance from Dunedin. And on the x-axis, I've changed it to time after midday. So what story does the blue line tell us? It says at midday, so it's time after midday, so that there must be midday. At midday, the train is 200 kilometres away from Dunedin. And what time does the train arrive in Dunedin? 4 p.m. Okay? So, what speed does the train travel at? What speed? Is it constant? Yes. It is constant because it's a straight line. It's not a squiggly line or anything. Constant speed. And the speed is 50 kilometres per hour. We could, because that's a negative slope, we could put a negative there that it's actually going towards Dunedin and positive being going away from Dunedin if we wanted to. How did we get the 50? We did rise of 200 over run of 4 hours. So in 4 hours it travelled 200 kilometres. So 200 kilometres, 4 hours, and that was 50 kilometres per hour. So rise was kilometres, run was hours, so it's kilometres per hour. Really important to get those units. So that's very cool. What story does the purple train tell us? At midday, where is the train? In Dunedin, correct. At 4 p.m, where is the train? 200 kilometres away from Dunedin. Fantastic. What's the speed of that train? Let's have a look at 1 hour. From 1 hour to 2 hours, that's 1 hour. Okay. And how far did it go? It went, what's this one here? 50. So it went 50 kilometres in 1 hour. So what's its speed? 50 kilometres per hour. But that's a positive speed. It's going away from Dunedin. It's going in the opposite direction. The blue train and the purple train, what time were they at the same place? At 2 o'clock. Fantastic. So that there is the intersection. And they were at the same place. What's the coordinates of that point? Yeah. So at 2 p.m, they were both 100 kilometres away from Dunedin. Okay? Nice. Give me the equation of this line. If we go y equals mx plus c, what's m? Gradient, same as speed. M is negative 50. Y equals negative 50 x plus y-intercept 200. Okay? Equation of this line. Y equals, oh sorry, that's the same line, different place. Equation of this line. Y equals, anybody? 50. Fantastic. 50x. This intercept is 0, so it's just y equals 50x. Notice when we got the gradient, we had to look at the numbers on the scale, you couldn't just look at the boxes. That's a real trick. The scales are not uniform. You needed to look at the numbers for the rise over run. This one here, tell me what speed is it going? So every 1 hour it's going a certain distance, and over 4 hours, this is very rough, over 4 hours how far did it go? That's 200. So over 4 hours how far did it go? Say again? Oh, hang on, that's actually at 100. That's at 100, 200. It went 100 over 4 hours, so it went at... How fast did it go? What's its speed? How far did it go in 1 hour? If in 4 hours it went 100 kilometres, 2 hours it would go 50, and in 1 hour it would go 25. So it's going 25 kilometres per hour. So can you see that this slope is not as steep as this slope? So this train is going slower than that train. Okay, equation of this line, y equals 25x plus what? What's the y-intercept? 100. Okay, so y equals mx plus c, m is the gradient, c is the y-intercept. This one here, what story can you tell me about the green train? It's not moving. So its speed is 0. So we could go y equals 0x, so 0 times x is going to disappear, plus, that's actually 70, isn't it? 0, 10, 20, 30, 40, 50, 60, 70. So y equals 70. Okay, doesn't matter what x is, y equals 70. So this train is sitting 70 kilometres away from Dunedin, going nowhere. We've talked about that intersection. What about this intersection here? What can you tell me about that intersection? I'll start the sentence. The red train and the purple train are both 200 kilometres away from Dunedin at 4 p.m. Which train is going faster, the red or the purple? The purple, steeper gradient, going faster. So which train overtook what? Purple overtook red. Okay? So this train was closer to Dunedin, now it's further away from Dunedin. Okay? This intersection, they were going in opposite directions. What about this intersection here? If the green train is broken down on the side of the track, then at what time approximately does the purple train overtake it? 1.5 hours is like 1:30 p.m, so maybe somewhere like 1:20 p.m, something like that. And at 2 hours, the purple and the blue are at the same spot, which is 100 kilometres away from Dunedin. The green's still sitting at 70, and the red one's the furthest away from Dunedin. It's about 150 kilometres away from Dunedin. This point here is, that's 2:30, 2.5 hours is 2:30 p.m. So after 2:30 p.m, just after 2:30 p.m, the blue train went past the green one. and the blue one was on the way to Dunedin. Okay, so what we've learned here is telling a story from graphs, talking about intersections of graphs, and also working out gradient in context, where the rise over the run gives the units of the gradient. Okay, so lots of information. So do that one in the beta textbook. That's very similar to this, to consolidate what we've just talked about. Okay, what page it is? Beta textbook, page 176, number 9. Going back to the GeoGebra one, I've shown the equations just to check our working. With the 25x plus y, oh, this is all the wrong way round, isn't it, algebra-wise? That's a different format to the format we did. So we can actually change that by going object properties, and with the algebra we can change that to y equals mx plus b. Change the format, y equals mx plus b, change the format, change the format. So equations can be in different formats. So there we have our equations. Did we get those right? Yes, we did. Okay, done.